As we did with our confidence interval estimates, we'll begin our study of hypothesis tests with the proportion. Let's look at the requirements. First, the sample observations are a simple random sample. We've seen that requirement now many times. The conditions of the binomial are satisfied. Recall that a research involving proportions is a binomial distribution. Let's look at those conditions. Fixed number of trials, outcomes in two categories, independent trials, and the probability of success is constant for all trials. So in a proportion, you might be taking a survey, getting some research on the number of left-handed people out of a population. Well, you would select your number of trials, your sample size N. Your outcomes are in two categories. Either the person is left-handed or they are not. The trials would be independent. One person's response to that question is not dependent on someone else's response to that question. And that the probability of someone being left-handed is a constant for that population. It's not changing as you're conducting your trials. So this is a binomial when we are conducting tests on proportions, as we said before when we were constructing confidence intervals estimates for proportions. And finally, we have to have at least 5 successes and 5 failures to make this a worthy test. If you don't have 5 successes or 5 failures, then you pretty much have the entire sample is one response, and that would not really be of much interest anyway. Okay. Let's look at the test statistic for our hypothesis test for the proportion. Okay, the test statistic is a Z statistic, as we've seen before. This is the Z distribution, and it would be our sample proportion, p hat, minus our population proportion over the square root of p times q over n. Okay, so that's the test statistic. And recall that we've talked about comparing, for our hypothesis test, the test statistic to the critical value. And that's one way we make a decision and draw conclusions in a hypothesis test. It's based on the results of your test. As you can see, the p hat is involved. The p is what your proposed or claimed claimed population proportion is, of course, because p is the population proportion. Okay, a couple of things to note. When we test claims about a proportion, the traditional method, which is the compare your test statistic to the critical value, and if the test statistic falls in the critical region, that is bordered by the critical value, we reject the null hypothesis. If it does not fall in that critical region that is marked by the critical value, then we fail to reject the null hypothesis. So that's one method. And then the p-value method, which is comparing the p-value with alpha. The p-value is associated with the test statistic, the probability associated with that. So there are 2 ways that we can make our decision, and either one of these ways will agree. These 2 ways will agree, will yield the same results. So what we will be doing, since we will be using the TI-8384 technology, is actually both. We will see each time that as we get the test statistic, compare that to a critical value, we'll have our p-value, we'll compare that to alpha, and those should always agree. So that's great. But other thing to note is, I've mentioned before that we can also use confidence interval estimates to make decisions in hypothesis testing. But when it comes to the proportion, the confidence interval method is not equivalent to the traditional method and the p-value method, and you may come up with a different conclusion. But we won't be using the confidence interval method as we proceed. It was mentioned before, though, that that is a possibility.